Charles's law, we saw temperature and volume. The independent variable that we changed was the temperature. The dependent variable, the thing that responded, was the volume. I don't know about you, but I noticed that when the temperature increased, the volume of the gas inside also increased. That is a direct relationship. Okay, it also has a mathematical relationship. Here it comes.
Left my folder.
Ladies and gentlemen, let's see how much you remember from Friday. What's the magic number? 273. What does that mean? To convert from Celsius to Kelvin, you add 273 to the Celsius temperature. If you want to go the other way, you subtract 273. Is that correct? All right. What do the variables that have a 1 near them mean? Those are the initials. That's what you're starting out with. So the first volume and the first temperature, you change one of these and the other one responds, yes? Okay. Can somebody tell me why you have to use Kelvin temperature?
You can't have a negative temperature.
Right. You can't have a negative temperature, and the reason why this is important is if you put a negative number into one of these temperatures, what kind of volume are you going to get out of it? A negative volume. Can you have a negative volume? No, you cannot take up negative space. Here we go. Here's your first problem. A balloon inflated in an air-conditioned room at 27 degrees C has a volume of 4.00 liters. If it's heated to 57 degrees C and the pressure remains constant, what is the new volume? First of all, stop. Is 27 degrees C a warm air-conditioned room, a cold air-conditioned room, or an okay air-conditioned room?
Okay.
It's actually a little hot. Yep, so 27 and 27 is 52 plus 30. It's about 82 degrees. That's kind of hot. So 57 degrees C, that's really, really, really hot. You don't want to be the balloon at 57 degrees C. All right. What's the new volume? What's the first thing you're supposed to do? List the variables. So we start out, the volume when we first start out is 4 liters. The first temperature is 300 degrees K. We did a little mental math there, 27 plus 273. Everybody's writing this down. Our V2 is what we would like to know. And our second temperature is 330 K. Without getting in front of the camera, send somebody in your row to go get the calculators. variables, we see that this is the formula. Now we're going to substitute in 4 over 300 is equal to x over 330. This is a cross multiply problem. 4.00 times 330 is 1,220. And 320 and 300x is our other side. I want x to be all by itself, so I'm going to divide both sides by 300. This cancels. X is equal to 1320 divided by 300, and that is 4.4. Is that a correct number? Liters. Okay, that works out. 4.4 liters. All right, and we are correct in using 2 sig figs. We have 2 sig figs in these. We're not going to count the sig figs when we convert. So that would be the right number of sig figs. Now, does this make sense? The first volume was 400 when the temperature, or 4 when the temperature was 300. We increased the temperature, so what should happen to the volume? It should increase, and our answer is 4.4, so in fact it did increase. So that was correct. Okay, here's one for you on your own. How many people have an answer? How many people got this? You know what, you're right there with me in getting the wrong answer. We had to convert everything to Kelvin, and we did. And then our answer came out, and it was in Kelvin. But the question actually asked for the temperature in Celsius. So here is the answer in Celsius. Did you get that one? All right, the next law that we're going to talk about is Gay-Lussac's law. Gay-Lussac was a Frenchman who did some work in Paris a number of years ago. Here's his law. What happens if you put an aerosol can into a fire? Boom, yep, it does. Because the volume is constant in that one. And if you raise the pressure too high, it will explode. So I went to a really weird restaurant over the weekend, and it was a 8-course meal, and none of the plates that they brought out were any bigger than this big. Not kidding. And one of the things they did was they took a huckleberry. Do you know what that is? Yeah. It kind of looks like a blueberry. And they dropped it in liquid nitrogen. Liquid nitrogen is very, very cold.
So it froze it basically?
Yeah, it froze the huckleberry just pretty much. And what happened to the huckleberry as it froze? It got all like shriveled and shrinky-dinky because it does have a little gas in it. And then they threw it into the bowl with other weird things, and then they put hot broth over it, and the huckleberry like expanded again. And I guess we were all supposed to be like, ooh, wow, but really it was just, liquid nitrogen, and the coffee came in a beaker, and the cream came in an Erlenmeyer flask, and everybody's like, okay, we've seen this. But one of the other things they did, they brought I saw them in the kitchen, and they were putting my food on the plate with a pair of tweezers. I had, for my main entree, 1 piece of broccoli. I'm not kidding. 1 piece of broccoli. Now, I'm not a giant eater, but really 1 piece of broccoli. Had to go home and eat. Okay. Here is a graphical representation of Gay-Lussac's law. Are we clear here? As the pressure goes up, the temperature goes up. What do we call this point right here on a graph? The origin. So the x and y values are both 0. So at absolute 0, what should the pressure be? 0. Why? Because that's what the graph says? No, you need to think of the reason that at absolute 0 there would be no pressure. Right. What are the particles doing at absolute 0? Absolutely nothing. They have stopped, haven't they? In order to have pressure, you have to have movement, and you have to have collision in the particles, and they're not colliding with anything. So, what other graph looks like this? The volume and temperature graph also looks like that. So if I were to change this, volume and temperatures like that, yeah? Right. Okay, and this would be Charles's law. Okay, let's do one Gay-Lussac problem, and then we'll do another demo. A gas in an aerosol can has a pressure of 1 atmosphere and 27 degrees C. If the can is thrown into a fire, don't do that at home, don't do that at home. What is the internal pressure of the gas when the temperature reaches 927 degrees Celsius? Should be working this problem out right now.